Another type of microwave filters is coupled, capacitively coupled series resonator filters. And capacitively coupled series resonators are usually used for bandpass filter types. Capacitively coupled series resonators is composed of capacitive gaps between printed line structure, and these capacitive gaps are connected with series resonators such that this transmission line section represents an open circuit resonator or a resonance circuit, and its resonance depends on its length or its electrical length theta 1, which corresponds to beta L1, and these resonators are connected in series. So the equivalent circuit for capacitively coupled series resonator circuit is transmission line of characteristic impedance Z0 connected in series to a capacitor with an admittance GB1, connected to a transmission line resonator of theta 1, connected to another capacitor GB2, and so on. In this case, we have N resonant series section of transmission line sections. This N section of resonant transmission line section with N plus 1 capacitive gaps. This N plus 1 capacitive gaps between them. The resonators, the length of these resonators are approximately lambda over 2 long. It is not exactly lambda over 2, and we will see how to calculate the electrical length for each resonator, but they are approximately lambda over 2 long at the center frequency omega naught. Effectively, it is required in the design of capacitively coupled series resonator to determine the value of the required capacitance B1, B2, B3, and from the required capacitances can be determined what is the separation between the gap of such transmission line sections. In addition, it is also required to determine theta 1, theta 2, theta 3, and from the phases of theta 1, theta 2, theta 3, it would be possible to determine the lengths of the resonator L1, L2, L3. So, if we have a gap delta 1 here, correspond to the capacitor C1, which has an admittance P1, so it is required to determine delta 1, L1, delta 2, L2, delta 3, L3, and so on. And the value of delta 1 can be obtained if I know what is the value of the admittance B or what is the value of the capacitance C. And the value of theta 1 would be determined, the value of L1 would be determined if I know what is the value of the required phase shift theta 1, and so on. Okay? Alright. As I said, this is the equivalent circuit for the capacitively coupled series resonator. This circuit can be represented in terms of constant line section of phase phi, in addition to another two line sections with phase shift phi 1 over 2, phi 1 over 2, phi 2 over 2, phi 2 over 2, phi 3 until phi n plus 1 over 2 to phi n plus 1 over 2, and so on. Such that theta 1 is given by phi plus phi 1 over 2 plus phi 2 over 2, and theta 2 is given by phi plus phi 2 over 2 plus phi 3 over 2, and so on. The advantage of this configuration is that we have here fixed transmission line section of phase phi, and these fixed transmission line sections are designed to have phase shift equal pi, so the length here is lambda over 2. So all the section phi has a physical length lambda over 2. Now JB1 is replaced by JB1 connected in both sides to a phase shift phi 1 over 2, phi 1 over 2. If we remember, the admittance inverter J, which has phase shift plus or minus 90 degrees, it can be represented by a transmission line section of a characteristic admittance Y0 equal J and electrical length lambda over 4. Another configuration for such admittance inverter is by using a series capacitance admittance JB connected to two transmission line sections theta over 2, theta over 2, where the value of J, the value of the admittance inverter, equals the value of the characteristic admittance Y0 multiplied by tan theta over 2. And the value of B is given by J over 1 minus J over Y0 squared. And the section theta over 2 and theta over 2, the transmission line section connected to such admittance or such capacitance, theta is given by minus tan minus 1 to be the value of the admittance of the capacitance over Y0. This means that the series capacitance can be adjusted to be an admittance inverter by adding transmission line section in both sides of the capacitance with a phase theta equal minus tan minus 1 to B over Y0. In our case, we are going to call this theta over 2 to be phi 1 over 2, phi 1 over 2 for B1, phi 2 over 2, phi 2 over 2 for B2, and so on. This means that phi I would equal minus tan minus 1 to B over Y0, which equal multiplying by Z0. So this is the transmission line section required to be added to the capacitance such that this combination would be equivalent to an admittance inverter J. And the value of B, or the relation between the value of B and J, is that B equals Ji, Bi equals Gi over 1 minus Gi over Y0, means that Z0 multiplied by Gi squared. This means that I'm going to replace each capacitor by a capacitor in addition to two transmission line sections, such that this capacitor with these two transmission line sections would correspond to an admittance inverter. And the first resonator, theta 1, is composed of half of this transmission line section connected to B1 plus phi plus half of the transmission line section connected to B2. This means that theta 1 equal phi plus phi 1 over 2 plus phi 2 over 2. And phi will be chosen to be pi. Or in other words, this section will be chosen to be lambda over 2. Okay? Now, we can start with this new circuit such that we are going to replace every B with its combined transmission line section phi 1 or phi 2 by an equivalent admittance inverter. So the resulting circuit would be admittance G1, which depends on the value of the admittance B1. So admittance inverter G1 depending on B1 connected to a transmission line section of phase shift pi or electrical length lambda over 2 connected to another admittance inverter J2 connected to a transmission line phi and so on. And the value of such admittance is given by the value of the admittance B. The value of the admittance inverter is obtained from the value of the admittance B. Effectively, this configuration has been studied before in the case of a coupled line filter. In the coupled line filter, we have the equivalent circuit as an admittance inverter J1 connected with a transmission line section of electrical length lambda over 8 or phase equal pi over 2, and this is connected by another admittance connected by another transmission line with a phase pi over 2. So the phase here, it was pi between the two admittance inverter. This was the case for the coupled line transmission line filter. This effectively is the same as here for the capacitively coupled resonator filter. We have inverters, and these inverters are connected by transmission line sections. This transmission line section of phase pi, which is the 2 theta equal pi, here is phi equal pi, and characteristic impedance Z0. So we are going to follow up the same analysis which we have done for the case of coupled line filter. For the coupled line filter, we said that this transmission line section of electrical length lambda over 2, it can be replaced by a parallel LC circuit L1 C1. And here we have the transformer, the admittance inverter. Then this is the admittance inverter in between, and the parallel LC circuit corresponding to the transmission line lambda over 2 and the admittance of the last resonator, the admittance inverter of the last resonator, and this is the load. So this is the equivalent circuit for the case of n equal 2, where we have 3 resonators. In this case, we have a transformer corresponding to the admittance inverter of the input, and another transformer corresponding to the admittance inverter of the output, and in between we have a resonance circuit corresponding to the transmission line section, this transmission line section, and another resonance circuit corresponding to this transmission line section, and in between we have an admittance inverter which corresponds to G. If we remember, we have calculated the input admittance for this network. We have calculated the input admittance of this network, and we said that the input admittance of this network is 1 over the turns ratio of the admittance inverter 1 multiplied by the input admittance of L1 C1, which is J omega C1 plus 1 over J omega L1, plus the admittance seen from the second inverter. The admittance seen from the second inverter is J2 squared over the admittance seen at the input of the inverter. The admittance seen at the input of the inverter was J square root C2 L2 multiplied by omega over omega naught minus omega naught over omega plus the admittance seen from this inverter, which is Z naught J3 squared. And by arranging the formula of this admittance, we obtain that the admittance can be arranged as 1 over J1 squared Z naught squared J square root C1 over L1 omega over omega naught minus omega naught over omega plus J squared over this term. On the other hand, the filter prototype of the bandpass filter for the second order filter, it can be represented as a parallel tank circuit of L1-C1- connected with a series tank circuit L2-C2-. And the values of L1-C1- L2-C2- are obtained from the prototype of the low pass filter prototype G1, G2. And we said that the input admittance for this circuit can be obtained as the input admittance of the first tank circuit J omega C1- plus 1 over J omega L1- plus the admittance of the second branch, which is 1 over J omega L2- 1 over J omega C2- plus Z naught, which can be arranged as J square root C1- over L1- multiplied by omega over omega naught minus omega naught over omega plus 1 over J square root L2- over C2- multiplied by omega over omega naught minus omega naught over omega plus Z naught. Now, by equating the input admittance of the filter prototype to the input admittance of the coupled resonator filter or capacitively coupled resonator filter, we obtain that this is the input admittance of capacitively coupled resonator filter, and this is the input admittance of the bandpass filter prototype. So by equating the corresponding terms, we can obtain that 1 over J1 squared Z naught squared multiplied by C square root C1 over L1. This would equal the square root of C1- over L-. And in similar way, we can prove that J1 squared Z naught squared over J2 squared multiplied by square root C2 over L2. This will equal square root L2 dash over C2 dash. And finally, we can prove that J1 squared Z0 cube J3 squared over J2 squared, this term multiplied by this term over this term would equal this term Z0. So we have three relations between J1, J2, and J3, and the corresponding values for the capacitance and inductance of the equivalent circuit of the capacitively coupled resonator and the corresponding capacitance and inductance of the filter prototype. By arranging this equation, we can obtain that we have these equations, which we have already proved. In addition, we know that the values of the filter prototype can be obtained in terms of the values of the low filter or low pass filter prototype G1 and G2 as L1 dash is given by delta Z0 over omega naught G1, C1 dash equal G1 over delta omega naught Z0, L2 dash equal G2 Z0 over delta omega naught, and C2 dash equals delta over omega naught G2 Z0. This actually the values of the bandpass filter prototype in terms of the values of the low pass filter prototype and scale to the input impedance and the center frequency and the operating bandwidth. In addition, this is the relation between the admittance transformation and the values of C and C dash and L and L dash. By combining these two relations, we can obtain that the admittance ratio J1 Z0 would be given by C1 L1 dash over L1 C1 dash to the power 1 over 4, and by applying the values of L1 dash and C1 dash and keeping in our mind that 1 over square root LC is omega naught and the value of L equal 2Z naught over omega pi and the value of C equal pi over 2Z naught omega naught. These relations already we have proved before for the case of coupled line filter, and the value of the square root L over C equal 2Z naught over pi from this relation, and the value of L dash over C dash equal delta Z naught over G. So we obtain that J1 Z naught equals square root by delta over 2G1, and J2 Z naught equal J1 Z naught squared multiplied by C2 C2 dash over L2 L2 dash to the power 1 over 4, which equals by delta over 2 square root G1 G2. Finally, J3 Z naught would equal J2 over J1, which is the square root of pi delta over 2G0, G2. Okay, so this is the admittance inverter values for second order bandpass filter for the case of capacitively coupled resonator. We can generalize this relation for a filter of order n instead of 2, such that the value of the first inverter Z0 G1 would be square root by delta over 2 G1, and Z0 Gn for n equal 2, 3, 4 until n would be by delta over 2 square root Gn minus 1 Gn, and the last admittance inverter, it would be Z0 Gn plus 1, it would equal square root by delta over 2 Gn multiplied by Gn plus 1. Now, by determining the values of the required admittance inverter, we can determine the corresponding required admittance Bi between the resonators. So Bi are given by Ji over 1 minus Z naught Gi squared. So if I know now the values of the required admittance inverter, I can obtain the value of the admittance between the resonators, Bi. And from Bi, I can obtain the required phi I, which correspond to the required transmission line section, which should be connected to the capacitor to obtain the required inverter. So phi I is given by minus 10 minus 1 to Z naught Bi, and it should be noted that phi I, it should be negative value. And if I know phi I now, I can obtain theta I. Theta I corresponds to the electrical length of these resonators. So theta I equals pi plus 1 over 2 phi I plus 1 over 2 phi I plus 1. So if I am talking about theta 1, I'm talking about pi plus 1 over 2 phi 1 plus 1 over 2 phi 2. Okay? Once I have got theta I can be represented in terms of Bi as theta I would be pi minus half 10 minus 1 to Z naught Bi, which corresponds to phi 1, plus 10 minus 1 to Z naught Bi plus 1, which corresponds to phi plus 1, phi I plus 1. Okay? So, by knowing the values of G, which correspond to the value of the low pass filter prototype, we can obtain the required values for the inverters, the admittance inverter. From the required values of the admittance inverter, we can obtain the required admittance Bi. Bi corresponds to the capacitance between the transmission line sections. This value actually determines the spacing between the transmission line section, delta. And from Bi, we can obtain the required phase shift phi I, and from the required phase shift phi I, we can obtain the electrical length of each resonator theta I. So this actually is the plan of the solution for the case of designing capacitively coupled resonator filter.